Good afternoon, and welcome to today's Electronic Design webcast. Our topic today, Improving Design Efficiency with Logic Devices, sponsored by TTI and Nexperia. I'm Bill Wong, Senior Content Director with Endeavor's Design Engineering Group. To begin, let me explain how you can participate in today's presentation. First of all, if you have any technical difficulties during today's session, simply hit F5 to refresh your webcast console. If you need assistance solving common issues, please click on the yellow help icon below the slides. This webinar interface allows you to resize the presentation by clicking on the maximize icon or by dragging the lower right corner to enlarge the window. Additionally, we welcome your questions during today's event. We'll answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send in your questions at any time. To do so, simply type your question into the question window on the side of your screen and hit the submit button. Also, please be aware that today's session is being recorded and will be available on the Electronic Design website within the next week. You'll be notified by email when the archive is available. Now let's meet today's speaker. Tom Wolf is a technical applications engineer or manager for Nexperia. Tom has designed automation systems for IBM and GE and provided application design engineering for semiconductor manufacturers Intel, AMD, NEC, and Philips, which is now at NXP. You can learn more about our speaker by clicking on the blue speaker bio widget in your console toolbar. Now let me turn things over to our presenter. Tom, the floor is yours.
And thank you for that introduction, and welcome to today's presentation on logic innovations for the industrial automotive space. My name is Tom Wolf, and today I'll be taking you a presentation on how to get cost savings out of an industrial system by using the newest innovations. So here's the agenda for today. What I'd like to do is base this on a case study, though. It's nice to talk about theoretical, but in this case, let's go ahead and look at a very specific example, an industrial controller, which we'll define in a second. Then we'll go into the very specific innovations themselves, the very products that are used for doing the cost reduction of the system. Then finally, this is the real important part of it, is show you both the direct and what I call the intangible cost savings of a system. Because obviously, if I can reduce the number of parts that you have to buy, that reduces the direct cost of the system. But there's many other system costs that you can save as well, too. Things like board cost savings and reliability and qualification. So we'll go into those in detail. So by the time we get to the end of this presentation, hopefully you'll see that taking a case study, in this case just one of them, or any example you have, and then applying these innovations to it, you will see real savings at the end of the design. So let's take our case study. In this case, we're going to look at an industrial controller. Now, hopefully you know what an industrial controller is, but let's do a little overview of it instead. An industrial controller is a specialized computer which is made for analyzing real-world input and controlling real-world things. So it's different than your personal computer, which is a keyboard and a display that a human interfaces to. An industrial controller interfaces to real objects, to real sensors, real machines, real motors in the outside world, often without the intervention of a human being at all. So it is a specialized computer with a variety of different inputs on it, outputs to a variety of different things you would find in a factory floor and an amusement park and all sorts of places like that where it's running a particular environment. It does have some graphical user interface on it because a human needs to tell it what to do. And it typically has some connection to the internet or to another network so that it can communicate data back and forth. Now, on the right side, I'm just showing a picture of some of the design features that you need in a machine, and I'm thanking National Instruments for their photo here, but all industrial controllers look sort of similar. They're not exactly exciting looking. They just have a bunch of modules in them that show you all the different features, and you plug in the parts you need depending on your specific application. So the design features. What is a design engineer worrying about or concerned about when he builds an industrial controller? Well, he has size constraints. It has to fit usually in a standard 19-inch equipment rack or some specialized format that that particular supplier builds. So there are PCB and package restrictions for it, and there's thermal restrictions. This machine may have to run on an iron foundry floor where the temperatures are very high or some other manufacturing environment. So there's almost always some thermal restrictions to this device. It may be very hot, very cold, but it is part of the design to compensate for where this machine will be used at. The most critical thing compared to maybe your home computer is that it's always on. Like I said, think of a factory which probably runs 24/7 for efficiency. It may be running, like I said, animations in an amusement park where it's running all the time as well too. So reliability is really critical for these. I need low power requirements because it does run all the time and that would create heat. I've got multiple power domains inside. The microprocessor may run at 1 voltage, the I/O board's at another, and then it talks to 24-volt solenoids and it runs 100-volt motors. So there's a wide variety of different voltages inside the system. And again, it is an industrial product. Your home computer reliability is different because if it blue screens, you just reboot it and start over. However, as an industrial product, it must have a very long lifetime. These machines are designed to run for 10 years or more continually, 24/7. So you need very high reliability on it. So these are the design challenges that come up when you're building an industrial controller. How do the logic innovations from Nexperia help the designer on these? And how do we go about saving costs for both the implementation as well as for the design and the manufacturing system? That's what we're going to look at today. So this is a list of the common logic that you might find inside an industrial controller. And this isn't theoretical. We actually went and looked at a number of industrial suppliers, some of the biggest ones in the world, and looked at the parts that they continually use. And these are the types of things that you find. Stuff like enable logic, which are buffer signals or Boolean algebra. They're the fundamental logic devices which have been around for multiple decades now. And on the right side are some specific part numbers. The 74 LVC family, one of the original 3.3 volt families, used extensively because everybody is low voltage, 3.3, and that fits. And so you see a lot of those parts around. The AUP family is a lower voltage version of that. So in modern controllers where the microprocessor is even lower voltage, you'll see AUP devices as well too. And then also some LV. LV, which we'll talk about in a little while now, like the that bottom part, the 74, LV74. The LVA family is unique in that it is a 5-volt family, so it's descended from the 1970s and 80s, but it has modern low voltage logic properties on it. So it has the energy efficiency properties of the AUP and the LVC family, but it has 5-volt interface for older devices. So industrial loves it because, again, they're still using 5-volt designs, but it's nice to get the efficiency of modern parts in them. So those are the type of logic devices you would see, the fundamental Boolean logic devices on board a typical industrial controller. However, you will also see a lot of translation logic, and we see more and more each year. A translator in logic is not like a human speech translator. It is a voltage level translator, sometimes called a level shifter. If I have a 3.3 volt device and a 5 volt device, they speak different voltage languages. A binary 1 in 3.3 is a different voltage than a binary 1 in 5 volt. So I need to have these level shifters or translators. Because industrial controllers have so many different voltage nodes in them, the micro runs at less than 1 volt, and I have 1.2 volt logic and 3.3 volt devices and 5 volt I/O. Every time I go from one of these voltages to another, I need to translate the voltage. So each year, more and more translator devices are being designed and being used because these controllers are stretching over many years. You want to keep using the 5 volt controller you designed 20 years ago because it really works well. You have to hook it to your sub 1 volt microprocessor. So you have to look at those things, and that's why these translators are becoming more and more popular. And then finally, there's other features too that come depending on the industrial controller itself. Things like analog switches and clock dividers, which we'll talk about. Specialized functions that are in the logic family, but may or may not show up in every single system. So there you have it. These are the common logic that you would find in an industrial controller. Again, there will be others, or maybe not every system will use these, but it's a good mixture of the type of things that the average, if there is an average industrial controller, would use. So now let's look at the logic innovations. All those features that we talked about, let's explain what they are so that you can see how they are used in a system and how each one of them gains you some obvious cost savings as well as some intangible cost savings. So these are the types of innovations I'd like to look at. Let's look at configurable logic. Hopefully it's something you've heard of before. If not, a real quick definition of that, both single and duals. Combinational logic. The GX family of logic packaging. This is a very small package. Again, more details in a minute on that. Clock dividers, the LV1T, that's 74 LV1T and 74 AUP 1T translator families. These are logic gates with translators built in, so you're already getting an interesting combination right there. Let's look at CB3Q switches, which are a high-speed analog type switch, translating shift registers, and there's that LV-A logic. Let's go through them one at a time so you see what these fundamental new innovations are. Remember that logic's been around since the 1970s, maybe the 1960s, but it is continually innovating, continually building new features, and that's what these new features are, things that the average designer may not know about, which really can improve the efficiency and reduce the cost of designing a system like an industrial controller. First one is combinational logic. Everybody uses logic in a design. That's what we saw in the original parts list for an industrial controller. Now, when you use these, each part has a different type of device in it. If you need an AND gate, you buy a device package which has one or more AND gates in it. If you need some exclusive OR gates, you'll buy another package that has exclusive ORs in it. Well, if you're looking for efficiency, that may not be the most efficient way of going about it. For example, OR gates come in packages of 4. You can get the singles, duals, quads, that call in one package. Suppose you don't need all of them in one package. I need one AND and one OR. Typically, I would have bought 2 packages. Combinational logic says, why don't we put 2 different types of logic inside the same package? So instead of buying one package for your AND, one package for your OR, 2 total packages, I put an AND and an OR together in the same package. I combine the 2 together. And that is the concept of it. So all the functions that I use all the time that used to be in discrete packages, now I can combine together to reduce the total number of packages that I have. And when we start getting into cost savings, you'll see how that's more than just getting rid of one package. I'm actually getting other benefits as well too. So combinational logic devices come in 2 different types. I can either get one where the devices are connected together, where in this case the 08 function and a 32, an AND and an OR function, they come together and they are connected. The end of one connects to the other internally to the device. Or I can get, as shown on the bottom, independent functions, where there is an OR gate and an AND gate in the same package, but they're not connected together. It's a fine point, but there's a lot of really interesting things you can do with it. Anyway, they're both combinational logic devices, and the benefits are is they immediately get a 50% space savings. I don't have to have 2 6-pin packages. I only need 1 package instead. So I cut the space down on the board quite a bit. I also get power savings. Every die has a certain fundamental static electricity, static power requirement to the device. It always consumes so much power. So just being there, whether it's doing a function or not, consumes a small amount of power. If I can reduce 2 packages to 1 package, then I reduce the power consumption of it. Sometimes I improve the speed. We'll look at that in a second, the examples that do that. And here's one of those intangible benefits for it. It's reduced assembly and material costs. Yes, I buy less parts for my bill of materials, but that means I don't have to assemble as many parts. I don't have to qualify as many parts. I don't have to test or repair as many parts as well, too. So that all adds into my system costs. So let's look a little more detail on it. Another function that is similar to this is the configurable logic device. A configurable logic device is sort of like a regular logic gate, but I can define its function depending on the way that I wire the part up. Now, a key thing, configurable logic is not programmable. I don't need a special programmer or any type of function for it. All of the devices are exactly the same. But depending on how I wire to the board, what pin I connect the voltage or what pin I connect a signal to, that changes the function of the device. So it can be a chameleon. It can be an OR gate in one place, it can be an AND gate in another, an inverter in a third place. But it's exactly the same piece of silicon. So again, from an intangible point of view, I have to buy one type of part, but I can use it in many different places, and it acts as a different gate in different places. And here's how it does it. The top diagram here shows you the internals of the -57 family. By the way, that's part of the part number, 74LVC1G57. Tells me where that number comes from. This is the actual circuit that's inside the device. It's no secret. It's a combination of gates. This combination of gates allows me to do configurability. In the lower left corner, I'm taking that exact part, LVC1G57, and I'm configuring it as an AND gate. Notice how I hook up the pins on the left side. The pin number A on it gets a VCC. I connect to the supply. I connect my A signal to one pin, B to pin C. So that's how I hook it up, and the output of the device is now at the Boolean function A and B. Now, if I take that exact same circuit, that exact same device, and I hook it up as shown in the lower right, where I now put A and B on different pins, and instead of hooking that third pin to supply rail, I hook it to ground, a different combination of inputs to it, I get a NOR function, A NOR B on it. Same piece of silicon, it's just the way that I wired it up. So that means one part on one corner of the board is working like an AND gate. That exact same part on another part of the board is working as a NOR gate. That is the benefit of using a configurable logic gate. One physical device can do more than one different logic function. And we have other functions as well too. That was the 57 family. There's also the 97, the 59, and the 98 function, or 58 function and the 98. All of these functions have a different base of parts inside of them. One might do ANDs, ORs, and inverters. One might do exclusive ORs, buffers, and some other Boolean function as well too. But they're all the same kind of idea. It's how I wire the part on the board will determine how that device functions. What is the actual logic gate that it implements on it? So you have a wide variety of parts on here that are available. All of these devices have Schmitt trigger inputs. Schmitt triggers are real important in the industrial space because most signals that come in have noise on them. They're not pure digital signals. So a Schmitt trigger will take that analog noise and will turn it into a cleaner digital signal. So they're very desired to have on the inputs of all of your logic gates. All of the configurable logic devices have them on board. So it's kind of a nice way of getting Schmitt triggers. There's not that many prime gates, just an OR gate or fixed as an AND gate, that have Schmitt triggers on them. The configurable logics have it. So sometimes it's best to just use a configurable logic because you get that Schmitt trigger for free. Otherwise, you would have had to have a different package on it. So it's already combining functions together. It combines a Schmitt trigger, which might have been a separate package, with your OR gate or your AND gate or whatever you've configured it for into a single package. Hopefully now you're starting to see how these new package innovations and new logic function innovations are reducing the number of devices that you need to look at. And that is the whole goal of logic innovations. I can use these simple devices to get considerable savings, which then ripples all through my entire design. Another interesting feature of configurable logic is something called the compound gate. Now, a compound gate means that there is another function on board which has a number of functions already glued together end to end. For example, most configurable logic devices have a total of 7 different functions on board. 5 of these functions are common, so you'll get like ANDs, ORs, inverts, and things like that. However, 2 of these 7 functions are called compound, so they're a little bit unusual. And one of the examples is in the 57 family, one of the 7 functions that you can configure it for is a NAND gate with 1 inverted input, which may sound really strange unless that's the function that you're implementing, in which case now it's already there. So I've now reduced 2 devices, the 00 function, 74 LVC1G00, and a 04 LVC1G04 is already free. They're already hooked together inside. So if I can implement these compound gates inside configurable logic, I can get quite a bit of benefit from these as well too. So another feature that you can use in configurable logic. This is a summary then of the 57 family. There's a similar chart for all of them, but what it shows you down the left side here is all the different functions which are available, the 7 base functions that this configurable logic can do. This is the name of them, and this is telling you the number of prime logic gates that would require to implement it. In other words, if configurable logic didn't exist, it would have taken you 2 discrete packages to implement this particular function. Notice this one package in the corner here that I could actually, it would take 3 physical packages to implement this one function. If that function's on your board, you can either use 3 separate packages by using it the old way, or you can use a configurable logic with compound function on it and get it all done with 1 package. That is some real savings that you could get. And this is how they work. The compound functions then allow me to hook together 2 chains together into 1 part. So in this case, a 1G57 would give me considerable board space because it would take what used to be the 1G14, the 1G32, 2 physical packages, which would have taken 2 6-pin packages. It now combines them into a single AUP 1G57, which, guess what? It's just a single 6-pin package. So you can do the math here pretty quickly. I've taken 12 pins in my package, 2 packages and 12 pins, compressed it down to 1 package and 6 pins. That is real savings, real part number savings and real board space savings in one place. The other stuff that I get is power savings from it. Remember, each one of these base functions requires so much power. In this case, an AUP 1G14 is a 0.5 microamps static. It consumes that much power just existing. And of course, the 1G132, it also consumes 0.5 microamps. What's interesting is that when I put these two together into a configurable logic family, the two parts together consume 0.5 microamps. In other words, I've cut my power in half as well too, because I don't have 2 packages idling. I only have 1 package idling at a time. And finally, with compound functions, I get speed improvements as well too. Because these two devices are connected end to end inside the same package, I don't have to have external buffers on them which slow the signal down. So here my 1G14 can run at 2.5 nanoseconds, that's the delay through the part, 2.5 nanoseconds for the 1G132, but when I combine these two packages together into one package, look, it runs at 2.9 nanoseconds. That's a 42% speed improvement as well too. So there's a lot of benefits of being able to take these two packages and compress them down into one package through the use of these compound or these combinational functions. So what does that give me? Let's summarize it. A single configurable logic device then gives me a smaller number of different devices purchased. Instead of having to buy an 08, a 32, an 07, all these different parts, as many as 7 different devices on my bill of materials, I can buy just one part and use that part in 7 different places. The other neat part is that means I buy as many as 7 times as many of the one part. That may move you a price column as well too. So it's a really nice feature from the procurement point of view. Reduces my bill of material and allows me to buy more of one part, which ripples through quality and inventory and a variety of other features as well too. Finally, I get higher quality as well too. Without getting too much into the details and the statistics of it, quality or reliability of board has to do with the number of failure points. If I had 12 solder joints because I had 2 6-pin packages, and I can reduce that to 6 solder points, I have reduced my number of points of failure in half. So overall, my reliability and quality will go up because I've now reduced the cost of that system. And then finally, just another word, there's also a device called a dual configurable logic. I don't need to spend much time on this because you already got it. It combines 2 single configurable logic packages in the same package. It's a combination configuration device. We need a new name for it, but essentially puts 2 of them inside. They're independently configurable. So inside a single package, I can configure one to be an OR and one to be an AND, or both to be ORs, or an inverter and a buffer, or whatever I choose inside a single package. So now my savings multiply even further than before. Now let's look at packaging innovations in general. This was a specific digital function we looked at, an electrical function. There's also ways of saving board space and cost by reducing the size of my packages. So you would think smaller is always better. Well, there's a point of diminishing returns. The problem is that as the packages get smaller, the pitch also gets smaller as well too. That means that the distance between the pins on a very small package gets really tiny. As that pitch gets too small though, it suddenly becomes very difficult to pick and place it because the pitch is so small and so exact. It becomes more difficult to solder without bridges. So there is some point where I can't make the pitch any smaller, even if I would like to make the package smaller. And Nexperia came up with an innovation for that. So here's that trouble again. The pitch again is the distance between 2 adjoining pins. Typically around 0.4 millimeters is where special soldering and special handling is required. Above that, pretty easy to work with. As this pitch though gets smaller and smaller because the total package gets smaller, it becomes more difficult to actually manufacture this device. And this is why. In a typical soldering mask, you're looking at it from the edge. Here's my PCB at the bottom, and there's the little contacts where I plan to solder my part down. This is a typical stencil. They're 100 microns thick. And what I do is I lay this over. It looks like a piece of thick aluminum foil with holes in it called apertures. And then I squeegee solder paste across the top of it, and the solder goes down into these little apertures and goes onto the board. So it's a nice way of spreading the solder where I want it, and then it doesn't go where I don't want it. As I get smaller and smaller, though, down below 0.4 millimeters, I need to do something special. Those apertures were too big, so I make the mask thinner, really thin, 80 microns. That's like thinner than aluminum foil. Very, very thin, very, very fragile. and I have to use a special solder paste. So my manufacturing of parts with very small pitch, tiny packages, tiny distance between the pins, gets more expensive, not because of the part necessarily, but because of the manufacturing process required to mount that part becomes more difficult, which is something that most manufacturers, frankly, would like to avoid. And the whole comes down to that step-down solder mask, and this is what they actually look like. Certain areas of the mask are hammered thinner, for lack of a better name, and those step-down areas then can only be in certain places, and also they're much more fragile. These masks wear out, as you can guess. The thinner they get, the more fragile they are, and the more careful I need to be with them. So most people want to avoid using step-down masks. You will if it's the only way to use the part. If you're building a cellular phone or a smartwatch and that's the only way to go about doing it, then you probably are going to want to use this. But for general manufacturing, remember, we're talking about industrial controllers, which aren't nearly as small. It makes more sense to stay with larger pitch, but I still want to have the smallest package possible. What's the solution for that? These are two competing things. Small pitch, I want a big pitch, but a small package. How do I go about doing that? And this is our solution. We call it the X2 SO-on package, the GX. It's also sometimes known as the diamond pack in parlance as well too. But this is a picture of it on the side here, and this is why we call it the diamond. Notice in the center, there's actually a square package in the middle of it that looks like the shape of a diamond. The reason this part works so nice is that the package size is very small. In this case, it is only 0.8 millimeters across the side. However, because the leads now go diagonally across the center, I'm drawing the biggest distance. So my minimum pitch is closer to 0.4 millimeters instead. So I have a very, very small package, but I have a pitch bigger than that magic 0.4. So it's easy to manufacture in the device. So we got the best of both worlds. Small package, but big enough pitch that I don't need to use something special for it. If you're wondering, by the way, that why this device is sitting on the head of a nail, that's not the head of a nail. That is the head of an average sewing pin, about 2 millimeters across. So this is what it looks like if you balance that part on the head of a pin. Very, very tiny package, but believe it or not, it's reasonably easy to manufacture this. It is not difficult to assemble and solder this part down. So I get a very, very small package on it. It's 36% smaller than the smallest GF or GM package, which is the smallest package before this one became around. I do not require step-down stencils. I have more flexibility in my device placement because I don't have to worry about where my step-down mask is. And finally, I don't need special solder for it. This is just a quick detail of it. I'll leave this here for your reading expertise later on. Gives you a function of it. Essentially, this new package, though, is available for virtually all of the low-voltage logic parts inside the Nexperia family. The LVC devices, the AUP we already talked about, and another family, the AXP. So it's treated just like that. I can get ANDs, ORs, inverters, buffers, everything in these very small packages. And it gives me the option of using these when I need very, very small package, but I don't want to have to spend the extra cost for high manufacturing. The next innovation is the voltage translation innovations. As we talked about, there's a lot of different voltage nodes inside an industrial controller. When I need to switch, for example, here between a 3.3 device, a PCMCIA card, which some people still use in the industrial world for storage, but I need to connect to my 1.8 volt applications processor. I need this translator, which will convert in this case from 3.3 to 1.8. So there are a wide variety of different devices available for it then. Because the different voltages are out there, there is the HEF family from 5 to 15 volts all the way down to these 1.2 volt devices. At each one of those, the actual voltage on and voltage for an on bit, a high, and a low bit are different voltages, and I need to compensate with a translator to convert the voltage from one family to the voltage of another. That is why we have this plethora of devices out there now, because we need to convert so many voltages from one family into another. Moving on then, this is a description of one of these devices. This is the 74 LVT1T family. It could be an 08, a 32, a 132. The key thing to notice in here is that T. We've added that in instead of a G, which would normally be a 1G. A 1T tells you that it has a translator function built on board. A lot of details on this page that you can read later, but the key thing is the 74 LVT1 family can switch between 1.6 and 5.5 volts. So any processor connection that I want to make between those, between an AUP family to an HC, between an LVC to an HC, anything that falls in those voltage ranges, this 74LV1T family is capable of doing both the function, an OR gate, an AND gate, whatever I need, and do the translation in one single part. Again, it's this whole idea of how can I reduce the number of packages that I have. Another family in the logic translation family is the 74 AUP group. And there it is again. See the T in there that tells you this is a translator device. This part, you can read the details about it later, but it can translate anything from 2.3 volts to 3.6 volts. Now you might be saying, wait a minute, that's narrower than the LV that I just looked at. Why don't you use the LV anywhere? Well, you don't always get something for nothing here. In this case, by narrowing the voltage from 2.3 to 3.6, I can get more performance out of it. It doesn't have to try so hard to work between it. So if you know your voltages fall 2.3 to 3.6, you'll get more efficiency, more speed, more power efficiency out of the device by going with the AUP. In other words, tune the particular translation device for your specific application to maximize the efficiency or the voltage of the device. The next one now I'd like to talk about is a translating shift register. Now, just briefly, this was based on the concept of a lot of people use this 595 function, which is a shift register. Serial data comes in, parallel data goes out of it. This part is used extensively in things like LED signage, the blinking LED signs or scoreboards and stuff like that. And so everybody was using the 595 function, but putting a translator in front of it. Here's the innovation for this. Nexperia said, let's take that shift register, a slightly more complex device, and put T, the translator, on the front of it. So we've combined two completely different functions together into one device to make it more efficient. Again, taking this idea of two devices and reducing it down to a single device, in this case, a translating shift register. Other features, other logic innovations we come out with along that same theme. Let's take two parts that people always use together and combine them into a single device. This one is called the AHC Logic Stage Divider. Forgive me for the name on that, but that means it is a 74 AVC something part number in particular. And what this device does is it simplifies the package size for a particular function which is used extensively. This is a divider. You send in a 1 megahertz clock. The first pin divides it by 2, so you get 500 kilohertz. The second divides it by 4, the second by 8, the second by 16. So every single one of those divides it down. You get a nice divisions of your clock. In reality, you don't use most of those, though. So instead of buying a part, having it divide 8 different ways, and you only use one of them, and you throw 7 pins away, we now offer a version which we take exactly the same piece of silicon. It still divides exactly the same way inside, but only one pin has been connected. Instead of having 14 pins, we only put 5 pins on it, and you get just the part which is divide by 16, or just the part which is divide by 8, or just by 32. So look at the savings you have. I have a much smaller package. Instead of a 14, I go down to a 5 pin, and every one of those pins is a place for reliability issues as well, too. So it's this concept, again, of logic innovations. If you're not using the pins anyway, why are you buying the pins? Let's give you an option where you get exactly the amount of logic exactly where you need it, which may be a good summary for all the parts we've talked about. Why take more part than what you really need? The next one, the CB3Q switches. These are used for very high-speed communications. If you want to have an external memory bus, an external SD card, an external PCMCIA, something like that, you may need the ability to switch very, very fast data. So what we've done is combine these parts together into a single device so that you have a high-speed bus for adding on extra memory on the outside of a particular microprocessor. And there's 2 variations of this. There's the old CBT-LV part, which gives you low-voltage devices, but it has to run at the same supply rail as the signals on it. The new family, the CB3Q family, can run at low voltage, but switch higher voltage signals. So again, it's that flexibility in logic innovations. What feature do you need? Let's build a part for it. And then finally, the LVA family, which we already talked about. LVA is a 5-volt family, runs at the old 5 volts established back in the 1970s and 80s, but it has the power down features and the energy efficiency of a modern 3.3 volt part. So it is the best of both worlds, and it's the same sort of thing. I can get translators in it, I can get OR functions, AND functions, everything that I need in it, but it gives me old voltage nodes, old voltage levels with new energy efficiency. So this brings us to the best part of the presentation now, where we talk about what are the real cost savings, the direct savings by reducing the number of parts that are in the system, but the intangible savings as well too. Those things which are maybe a little harder to measure, which I think you all will agree, have a cost savings when you can implement these particular innovations. So from a direct cost benefit savings, let's look at the different devices here. I can get package count reductions. Anytime I can remove a package, I'm saving money. Let's face it, most packages all cost about the same amount because you're really paying for more package than silicon at this commodity level. So if I can get rid of a package, that is a very specific amount of money that I can save on my bill of materials. So the devices, the innovations which give me package count reductions, I can use combination logic, which will reduce my package count by as many as a third. There are some cases where I can take 3 functions, which used to be 3 packages, and combine them down to 1 package. It's a third of the size of my previous system. My single configurables can reduce package count by as much as 3 again, if I pick one of those functions, which is the compound configurable devices. If I use a dual configurable, it will reduce my package count by as much as 1 in 6. If I can take each of those functions, implement 3 packages by each half of it, that's 6 packages I can theoretically replace with 1 package. That is real savings in terms of the number of parts that I'm buying. I also get package cost restrictions. Remember the parts, again, parts that are in the same package cost roughly the same amount. So by combining them together, I'm reducing my cost proportion at the same time. And even more important, which we really didn't talk about here, there are new package types which have even more potential for cost savings. Ultimately, the cost of a package is the amount of material in it. A smaller package, after amortization and research and everything is all amortized in there, the size of the package determines the cost. So a package which is half the physical amount of material will ultimately cost less, maybe half of what the package does. So by going to some of these smaller package types, I'm saving real material and again, saving real dollars on them. And then finally, there's the PCB board saving space. If I have a lot of logic gates, and we may have, from 5, 6, a dozen of them in a very small package, being able to reduce my PCB by getting rid of the number of devices, by making my board physically smaller, I'm saving on raw PCB cost. It costs so many pennies per square inch. I'm reducing the number of square inches I need for my board, and I'm saving there directly. The other side, too, is that a smaller PC can fit inside a smaller box. So my entire function may get smaller. If I'm doing things like consumer products, this is really critical. My smartwatch can get really, really tiny if I can reduce the package, reduce the PCB, the watch gets smaller. But even at an industrial controller space, each module, each card can be smaller. I can embed them. I can put more of them into the same equipment rack. So I can get real savings from a system point of view by putting more functionality inside the limited space that I may have available. Now, this is the final one, the intangible savings size. These are the costs which are not directly seen in the cost of the part that you get from Nexperia. It is the cost that you save in your manufacturing. For example, deliberately in the manufacturing savings itself, when I combine functions together, I reduce the number of packages that I have. Each package takes a certain amount of time and cost to pick and place. The number varies depending on your particular manufacturing assembly, but there is a cost. Every part I don't have to pick and place saves me money in my manufacturing equipment. So configurable logic will also reduce the number of unique reels that I have to have. If you think about how pick and place machines are done, there's reels of all the different parts on board. There's only a limited number of reels, however. If I've got more different parts than my machine can handle, I may have to do 2 passes through pick and place. Configurable logic, because one part can do more than one function, one part can replace up to 7 reels on that machine, I may reduce the number of passes that I have to do for my pick and place equipment. So it can be a real manufacturing time savings. 1 pass through the machine instead of 2 because I've reduced the number of different parts that I have to have on the machine in the first place. The next intangible saving is qualification savings. Every part that you put into a critical environment like an industrial controller needs to be qualified for that application. There is a cost for qualifying. It may be as much as the data sheet looks fine, let's use it, up to hundreds of thousands of dollars to qualify for a mission critical device. Obviously, the fewer parts that I can have in my system, the less number of qualifications I have, and then I don't have to amortize that qualification cost across more parts. I get instant savings from reducing my qualification. I get power savings by reducing the number of parts as we've shown. I may be able to reduce either my power supply or just the power regulation circuit on board. The size of my Zener diodes go down, the size of the voltage regulator goes down. It ripples out. It may not be large, but even saving a few pennies on a board that I make thousands or millions of a year can be real system savings across the life of the entire product. And as we mentioned before, you get reliability savings. The pin contacts are a potential failure point in a design. So the number of packages I can reduces the number of pins, reduces the number of failure points, improves the quality and reliability of my system. Finally, if I do get failures, which I do, my rework costs go down as well too. Reworking a 0.4 millimeter, sub 0.4 millimeter pitch device is not simple. It takes a microscope and steady nerves to do that. If I'm using bigger packages which are easier to rework, my cost of reworking, of servicing a board or fixing one that failed in manufacturing goes down as well too. So I save those boards. They're not thrown away. I have the ability to repair them easier and I get that savings. And finally, I get inventory savings as well too. Wouldn't it be nice not to have a gigantic warehouse with all these different parts? To be able to use configurable logic or combinational logic to reduce the number of different devices in the warehouse so that stocking of those parts and having to keep track of them and all the assets and all the costs associated with inventory reduces as well too. So it's hard to put a dollar on each one of these. I can tell you what it costs to go from one package to two if you're only just buying the part. These intangible savings, though, really multiply out when you build thousands or tens of thousands or millions of units. These pennies saved here or these dollars saved here in manufacturing quickly build up and give you a wonderful savings, which is far beyond the price savings you got from a single device. So now I challenge you. We looked at the industrial controller. What is your case study? Where can Nexperia Logic Innovations help save you as well, too? And with that, including the formal part of my presentation, I'd like to open it up for questions and answers at this time. Thank you very much.
Great. Well, a few of you have already submitted questions, so we're going to jump right in. If you'd like to submit a question, type your question into the question window on the side of your screen and hit the submit button. While we're answering your questions, please complete the feedback form, which is located at the bottom of your screen. First one's pretty easy. Do these devices have open collector or open drain outputs?
Thanks, Bill. Yeah, I saw that question come in sometime around to the configurable logic. The configurable logic devices themselves, there is no open drain version of those. The 9899 series does have a tri-state output. There's an enable pin on it, so I have that. If the question, though, was regarding logic in general, oh, yes, by all means, there's plenty of open drain parts across a wide variety of devices here.
Okay. How did you measure the intangible cost savings in a system?
As I expressed in the presentation, I can do a really good job estimating the cost of savings of the Nexperia parts. If you had two 6-pin packages and you went to one 6-pin package and each package was 5 cents, the math's easy there. So that is a simple look at the price list of the part you buy from us and I can tell you the savings. Intangible is more complex because it really depends on your specific manufacturing process. Is the manufacturing done in-house? Is it done offshore? Is it done by a CM? What is the cost of each one? So we can give you an estimate of where you can look at these savings at. If you reduce the requirements to get rid of a step-down solder mask, you don't have to use special solder, there's a real cost to that. The mask costs different, the solder costs less. Amortize the cost of that mask across the 10,000, 100,000 million boards that you cost, and there's the number that you get, but it will be unique for each manufacturer. The biggest one that we find is in the qualification process, getting rid of the paperwork. If you only have to qualify one part instead of two because you've combined them, or qualify one because you've used a configurable logic device that replaced 5 parts, qualifications are expensive. As I said, the presentation or the actual qualification may cost anything from the design engineer says, it's good, let's go ahead and use it, 0 cost, all the way up to a full automotive qual is in excess of $100,000. Amortize that $100,000 saved across your 100,000 boards, it's $1 a board. I mean, it's a huge number at that point, but it will vary from person to person, specific application.
Okay. What programmers support your configurable logic devices?
Oh, that's always a confusing question. When we call them configurable, it's, oh, you must program it. No, there's no programming for it. Every piece, every 74 AUP 1G57, every single one of them are identical. They're always identical. You solder them on the board, they're still the identical electronic circuit. It's because of the way you connected them on the board. Maybe a better name would be a PCB configurable name, because it's the way you use it, not the way you change the part itself. So there is no programming required for it. There's no programmer, no JTAG, no nothing on it. You just take the part, put it on the board, and it's the way you've routed the signals to the part, which will determine should it behave like an OR gate, an AND gate, whatever you've defined. There is no programming needed.
Okay. What is the maximum package savings you can get from dual configurable logic, and what is the typical savings?
That's always a good one. It comes down to statistics. There is one extreme example in dual configurable logic. If you take one of the parts which requires Schmitt trigger on both inputs, one inverted output, NAND function, external drive on it, and then you double it, it turns out that there's one theoretical case where you could replace 10 discrete device packages with one dual configurable, 10 to 1. It's not going to happen. I haven't seen anybody do it yet, but typically it's 2 to 3 to 1. So, I'm taking 2 to 3 packages I had on my board, I reduced them down to one part, so 2 to 3 packages become one package. That's still a good number. If you've got that one unicorn of a design out there that happens to use that one circuit, you could, in theory, get a 10 to 1. I'd love to see it.
Okay. How do you rework the Exxon 2 package since it's so small?
It sounds like it's small, and that picture was real. That actually is the die sitting on the head of a pin. It's a very small part. I will tell you, and I don't think I'm bragging that much, I have manually reworked them. First, you don't have any coffee in the morning, get steady nerves, and you need a microscope to see the part. That's kind of the given. But in reality, a 0.4 millimeter pitch is not that extreme. A lot of much larger packages, a lot of the gull wing and a lot of the leadless parts that are out there, they have 0.4 millimeter pitch, and we don't really get scared about those. This one is just scary because it's 0.4 millimeter pitch, and the whole package is only 0.8 millimeters on the side. So yes, with steady nerves, you can rework them. Of course, when you're soldering parts like that, everybody knows you don't solder each pin one at a time. You use a heat plate or a heat gun, and you solder all 4 or all 6 pins simultaneously. So yes, it can indeed be done. The hardest part of them is putting the part on the board and remembering not to breathe, because you'll blow it right off the board onto the floor of the lab, where I have quite a collection of them already.
Okay. Why do you have so many level shifter devices with overlapping power supply voltages? Why not just one part for all the voltages? I suspect it's a little bit harder than that.
Yeah, you're right. There's so many different translators, the level shifters or the translators. It's a growing family, which of course has occurred over a period of many years. Now, you're right. It seems like you should take the one part, the AXP family, the 74 AXP 1P45 is one of the parts. You think, gee, let's use it because it can shift anything from 0.8 volts all the way up to 5.5. I'll use it for everything. Well, you never get something for nothing. The speed of that part, of that translator, is going to be slower than a part with a much narrower range on it. In other words, I can make a part with a very narrow range on it, which will be much faster and optimized for that application. A general purpose one, where my speed is not in essence, then I could get a part with a wider voltage on it. So we give it the option for both. Take one that is slow and very general purpose. Wonderful, you've reduced your bill of materials. But if you've got an application critical place, maybe you want to go with an AVC, which is a CMOS bipolar function, 1P45 function, which is very narrow, relatively narrow, but very high speed. So it really depends on the application.
Okay, here's sort of a general question. Could you comment on long-term availability of the components?
Absolutely. As a matter of fact, we're so proud of our longevity is that we publish it on our website. Go to nexperia.com under support and look for longevity. And what we do is we actually list how long each part will be available. Design it in today, and the majority of parts will be available for 10 years. In exactly the same package, same function, you can buy the same part in the year 2030 as you buy today. And every year we review that, so it's a rolling window of 10 years. And we can say that confidently because a lot of our parts that we built, some of our HEF family parts, which are the CD4000 metal gate family, invented in the 1970s, the exact same part is still in production today. So we have some parts that have been around for 50 years. To project forward 10 years, it's not that difficult. But again, look at our website. We're proud to say when you pick a part today, it's probably going to be around for 10 years. In reality, it'll be around until people stop buying it. We'll keep making it until you don't want it anymore.
Okay. Are any of them automotive qualified?
Yes, we have an entire line of automotive logic qualified parts. Matter of fact, some of the configurables are, a lot of the functions we talked about are today. In logic, it's easy to determine if the part is automotive grade or not because we put a dash Q100 on the end of it. So the 74 LVC 1G07 GM dash Q100, I know that it's passed full AEC Q101 certification. The real secret, or not a secret, I guess, every one of our processes, every one of our parts is designed so that it can be automotive grade. Now, the difference of a commercial and an automotive grade part is that automotive grade part has a paper trail. It's got the lot numbers on it. It's got a PPAP review. It's got a number of different paperwork requirements that the automotive industry requires, but the silicon is the same. So all of our parts are automotive grade, but from a technical point of view, they only become full automotive grade when we put the paper trail on them that follows it. So it's not a technical issue, it's a paper trail issue. But yes, almost all these logic devices have an automotive grade version available of them.
Okay. If below 0.4 millimeter pitch requires special mask and solder, does Nexperia even make devices with pitches smaller than that?
Oh, yes. 0.4 millimeter is that point where most manufacturing lines, it gets difficult. So that's kind of the lower threshold for most manufacturers and most designers. But no, we make parts smaller than that. We've got 0.35 millimeter pitch, 0.3 millimeter pitch. There's a 0.22 millimeter pitch device out there, which is used for, as you can guess, cell phones and watches and things like that. And then there's die construction, which is even finer than that. So for those people that really need the ultimate smallest, we build packages which in some cases there's only one or two assembly houses on the planet that can handle them, but we will build them. What we're trying to do though is make this technology available for the masses, for the average contract manufacturer, the average assembler, and that's what the Exxon 2 part was built for, to have a part which is the absolute smallest package that you could make, but can still be assembled on a regular assembly line, and that was its target. But no, you want to go smaller? Yep, we've got even tinier packages.
Okay, well, I'm afraid we've run out of time. If you asked a question that we haven't gotten to, we'll be in contact with you soon to answer all of your questions. This concludes today's presentation. On behalf of Electronic Design, I'd like to thank TTI and Nexperia for sponsoring today's event, and of course to all of you for joining us. Have a great rest of the day.